Welcome everyone to the fourth DWL workshop and its webinar Etch series. Today we have David Graves from Princeton University, and this is webinar 4 out of 8. Before I hand over to David, I'd like to do a few acknowledgements. First, I'd like to recognize the traditional owners of the land we are gathered here today, or at least I am. I wish to acknowledge the people of the Kulin Nations on whose land we are gathered today, and I pay my respects to their elders past and present. Furthermore, I'd like to acknowledge Jane Fitzpatrick and the Australian National Fabrication Facility for their ongoing support. Also, I'd like to acknowledge all the people you see on the left-hand side, especially for today's webinar, the NNCI Etch Symposium, for their ideas and suggestions for possible presenters, which made today's webinar possible. As I said, it's webinar 4 out of 8. We have an additional webinar, which is scheduled on the 19th of February. And this is done by Lena Wolf from AXT, Focused Ion Beams for Nanofabrication. What happens when the ion hits the sample? Also, I'd like to mention our sister conferences and workshops. This is one event organized by the Focused Ion Beam Special Interest Group. And this is held 9th of February, which is a week after the direct write lithography workshop, organized by Lena Wolf and Anders Barlow. And of course, our collaborators from the Zurich Nanofabrication Days, 3Beams meeting, the NanoFab UK network, and the meeting for advanced electron beam lithography, MABEL. And finally, big shout out to the organizing committee for their hard work they put into making this workshop and the webinar series possible. So today, it is my pleasure to introduce you to David Graves, who joined the University of California at Berkeley Department of Chemical Engineering in 1986 after receiving a PhD from the University of Minnesota. He retired from UCB in May 2020 and served as Associated Lab Director at the Princeton Plasma Physics Lab from 2020 to 22. He's currently professor in the Department of Chemical and Biological Engineering at Princeton University. His research interests are in plasma materials processing and other applications of non-equilibrium, low-temperature plasma phenomena. He's a fellow of the Institute of Physics and the International Plasma Chemistry Society. He was first Lamb Research Distinguished Chair in Semiconductor Processing at UC Berkeley. He received the Ellis Prize for the study of ionized gases from the American Physical Society, the Dry Process Nishizawa Award, the Plasma Materials Science Hall of Fame Prize, the IS Plasma Conference Prize, and the Plasma Chemistry Award from the International Plasma Chemistry Society. So David, as I said, it's my absolute pleasure to welcome you today with atomic mechanisms during plasma etching. I'll stop sharing and hand over to you.
Okay. So let's see. Everybody see you can see the slide, Michael?
Yes, I do.
Okay.
Perfect.
So thank you so much for the introduction and also for the introduction to, or the invitation, I should say, to present to this group today. Yeah, so the main focus that I wanted to talk about is to discuss the progress that our community, I'll focus primarily on our own group's work, that our community has made in actually predicting what happens at a surface exposed to low temperature plasma, especially in etching. If you know the species that are impacting the surface, the energies, the angles, and the relative fluxes, is it possible to predict a priori, just knowing the materials and the chemistry, what is going on at the surface? And we've had some success in that, and I want to describe the approaches that we've taken. So the outline of the talk today, just a very brief introduction to plasma etching and mechanistic understanding. I think probably most of the people in the audience have some familiarity with this already, of course. And then I'll jump into the so-called site balance models, which are a phenomenological model that's been used. I'm not sure this has been discussed in your series so far, to predict surface chemistry. It was borrowed from the catalysis community. It was adapted for the case of plasma processing. and then discuss the experiments that are particularly useful in exploring these fundamental mechanisms, the ion neutral beam experiments, where you're impacting a surface in a low pressure environment with controlled known fluxes of species, ions and neutrals in this case, and then the development of this concept of the ion neutral synergy, which emerged in the late 70s, early 80s, especially from the work of John Cobert and Harold Winters at IBM. Then I'll get into the meat of the predictive capability using molecular dynamic simulations, describe what those are, the role of interatomic potentials. There are challenges in length and timescales when using these atomistic simulations. When you talk about that, I'll show some examples. And then show a comparison of MD simulations for some of the selected chemistries that I'll describe to various experiments and discuss a bit the mechanisms. We've been able to reproduce those experiments. And then I'll go into the example of plasma atomic layer etching, particularly the case of silicon in the presence of molecular chlorine, not a chlorine plasma, but molecular chlorine, and then followed by argon ions in comparison to experiments. And the experiments were done by my colleague Vince Donnelly at the University of Houston, and we're able to make some comparisons there. You can see the kind of agreement we're able to get from with the MD simulations and the experiments. And then I'll use a second example, something we've looked at most recently, which is atomic layer etching of diamond carbon, in this case in the presence of argon ions, but also energetic O species. And then finally, I'll have a few concluding remarks to talk about some of the current limitations of this sort of approach, some of the uncertainties that we know are there, and where we think there are some future opportunities to advance the field. So I'll start with this very brief review. I actually borrowed these from Sungbo Shem, who was a visitor from Samsung a couple of years ago at my group at Berkeley. Perhaps, of course, you already know this, but reminding us all that the sort of processes we're dealing with begin with lithography, exposing a photoresist through a mask, followed by development. And then the next step, of course, is plasma etching, where the resist ideally is perfectly resistant to the plasma, and you can etch the underlying film, ideally again with perfect selectivity to the underlying material, and then you strip in the clean. So, of course, what we're interested in today is this step of plasma etching, and specifically on the way that plasmas interact with surfaces. There's a very complex problem. There's a lot going on. The plasmas are not simple. Of course, these kinds of plasmas are also used for applications in film deposition and cleaning, among other applications. Again, using these slides that Sungbo let me borrow from one of his presentations. And now the plasmas, I borrowed this sketch from Mark Kushner at the University of Michigan. The plasmas we're dealing with are in enclosed spaces, of course, excited by external radio frequency power supplies. This one shows an example of a coil on the top with the first RF power supply, and then a couple of additional ones, RF1 and RF2, applied to the substrate where the wafer is located. And the little schematic is intended to show that just a couple of the many dozens, if not hundreds of elementary collisional reactions include things like molecular dissociation of chlorine into chlorine radicals and ionization of argon to form Ar plus. And the idea is that the combination of the impacting argon ions at the silicon wafer in the presence of the chlorine radicals results in etching, in this case, in the formation of this SiClN species, which then gets pumped away. This is the basic idea. We're focusing specifically on what's happening not in the plasma, but at the surface, in this case, the silicon wafer. Now, there's a lot going on in general. I took this sketch from a report that came out a couple of years ago that we did for the Department of Energy, this report on the science challenges and research opportunities for plasma applications in microelectronics. You can get this report. We tried to identify what we think some of the real key opportunities are in the industry today. This is available online. And the sketch that Iray Idle at NYU did for us sort of just kind of gives you a little bit of a taste. There's sputtering occurring. There's ions that can implant, ion-assisted etching. I'll talk more about that. Chemical etching, meaning neutral species reacting with the underlying film. Ion or photon, for example, UV photon-induced damage, photon-assisted etching, and electron-assisted etching. Now, I'm not going to talk about photons and electrons today. We're talking about just neutral radicals and ions. But we know some of these other energetic species can play important roles. I think I didn't include here actually electronically excited states or vibrationally excited states. Translationally excited species can sometimes play a role. The plasma, of course, as no doubt you probably are aware, is highly non-equilibrium. You can't characterize the energies with a single temperature. So there's a lot going on, and what's happening at the surface is not well understood. So what I'm talking about today is an attempt to put some order into this sort of chaotic situation. Are there situations where we can actually predict a priori what's going to happen at the surface given the species? And again, so I'll focus on ions and radicals, but the plasma is complex, and of course, there's a lot more hitting the surface than just a radical and an ion, as I mentioned. And some years ago, in fact, this goes all the way back into the late 70s and early 80s, and this was from Jane Chang's dissertation at MIT, where she was advised by Herb Son. She graduated in 1997. So it's sort of a schematic of a vacuum chamber, so-called vacuum beam system in which there's a probe, in this case, an ion flux probe. You could also use a neutral flux probe to measure chlorine atom fluxes. But in the idea then is if you can deliver and control the fluxes of known species, in this case, chlorine radicals, chlorine molecules, argon ions coming through another port. These are external sources of ions and radicals that can spray onto the surface. And she also looked at this etch product SiCl2 coming in. And by varying the energies and the flux ratios of the different species, and then measuring things like etch rates, in some cases you can measure surface properties and etch products coming off. Although in this case, I'll just show you some etch rates that she measured. What Jane did was she developed a phenomenological model based on the site balance concept that I mentioned earlier. And then she used the experimental results to fit the parameters in that phenomenological model. And as we'll see, the molecular dynamic simulations, which rely only on the properties of, say, chlorine, argon, and silicon, are able to reproduce those results fairly well. But I'll get into that in a little bit more detail in a minute. Yeah, so the idea here is that this is really kind of a simulated plasma surface experiment. This is not a plasma per se, it's a beam system, but it allows a good control of the fluxes in the species and are the conditions under which you can most directly compare to your, say, molecular dynamic simulations, because in the simulation you're bringing in various species at different ratios and different energies. And this kind of experiment is able to give you the results that are closest to those assumptions compared to a plasma, where there's a lot more going on. Now, I'll go back to an earlier beam experiment that was reported in 1979, this famous paper that John Coburn and Harold Winters published when they were at IBM Almaden in South San Jose. So they were using a similar kind of beam system. They used a quartz microbalance. They put a silicon film on it. And some of you may be familiar with this. They sprayed argon ions and xenon difluoride neutrals. But the xenon difluoride is just it was a convenient way to bring fluorine into the surface rather than, say, F atoms or fluorine molecules. The xenon difluoride would fall apart pretty readily on the surface at room temperature. So it was a convenient way to bring in fluorine neutrals. And then they looked at the etch rate as a function of these different fluxes. And I've sort of redrawn their famous plot here, but so they plotted etch rate versus time in their beam system. And when they had only the argon ions, they saw a non-zero etch rate. This is just from the physical sputtering. I think it was like 450 EV argon ions or something like that. And then they turned on the xenon difluoride with the argon ions, and the rate jumped up by almost a factor of 10. There was a little transient and it kind of stabilized out. Then they turned off the argon ions and had only the neutral radicals, and there was some spontaneous etching. The fluorine from the xenon difluoride would etch the silicon. This was undoped silicon at room temperature. It would etch at a finite rate. But it was the combination of the ions and the neutrals, the so-called ion-neutral synergy. There's some kind of nonlinear effect that's occurring. So if you add up the etch rate from the argon ions alone and from the fluorine radicals alone, it's much less than the combination of the ions and the fluorine together. And they immediately realized, because of course they knew perfectly well that the ions from the plasma were coming in perpendicular to the surface, that this was a way of explaining the observation that plasma etching could give you anisotropic or directional etching, just etching the bottom of the feature as opposed to the sidewalls. The fluorine may come bouncing around and it may etch spontaneously, but most of the etching is occurring at the bottom. The bottom of the feature, you get both the ion bombardment and the fluorine flux. And so this ion neutral synergy very quickly became kind of the prototype concept of how plasma chemistry is occurring. Now, John and Harold published a bunch of papers where they did various experiments where they tried to understand, well, what were the ions actually doing? Were they increasing the adsorption probability of the fluorine? Were they increasing the rate of product formation, et cetera? And I won't go into great detail on that. But the bottom line was they and others later showed that if you plot the yield of silicon in these experiments, and recall that the yield of silicon is defined as the average number of silicon atoms removed per incident ion. And they discovered that the key was the ratio, the flux ratio. So the neutral JF is the flux of the neutral radicals, J plus is the flux of the argon ions, and this yield as varying as a function of the flux ratio and at different ion energies from 20 eV, 500 eV, 1000 eV. This is what determined the sputtering yield was the flux ratio and the energy of the ions. One of the tasks then, and I'll go through it briefly in its simplest manifestation of the site balance model is to show that you can reproduce precisely this kind of plot, which you may recall looks a bit like a Langmuir uptake, like a Langmuir isotherm, or in some cases in catalysis, people have used the Langmuir-Hinshelwood model, which is we'll see is based on some similar ideas. So let's just briefly remind ourselves about this Langmuir surface site balance model. This is no ions now. This is just you have reactants R in the gas phase with some partial pressure P sub R. And we'll define theta as the fraction of the filled site. So the surface is assumed, this is the Langmuir's concept, was that the surface has a series of discrete reactive adsorption sites. And a reactant R can come in and react with this bond, with this open site, and fill it.
Raul is missing your t-shirt.
And the reaction rate then in this model is proportional to the coverage through some reaction rate coefficient. So we need to get an expression for the fraction of filled sites, this theta. And if you assume that what's governing the steady state fractional coverage is an equality of rates of the rate of adsorption, where there's a adsorption rate coefficient multiplied times some concentration, in this case the partial pressure of the R, times the fraction of open sites, which is 1 minus theta. You say, well, that's the rate at which the fluorine, whatever the reactive species is going down, and the rate of desorption is some constant times that coverage. If you simply solve the algebraic equation for the steady state coverage, you get an expression like this. So then if you say, well, the rate of reaction, this is this sort of simplified first order surface reaction that Langmuir was imagining, the rate of reaction is some rate coefficient, K reaction, times this surface coverage theta. If you plot theta versus the partial pressure of the reactant, you get this classic Langmuirian curve where it saturates out at 1. And you can see then that when the partial pressure is low, the reaction is limited by the flux from the gas. Okay, but when the partial pressure gets high enough, essentially the R coming in from the gas is saturating all of these available sites, and so the coverage saturates at 1, and the rate then is its maximum value. So if you go back a couple of slides here to this plot, you can see that in some ways this is looking kind of similar to that. And a number of people in the community back in the 80s said, oh, maybe this would be a good way, would have to modify this surface site balance model, but maybe we could use this kind of phenomenological model to explain the observation of this ion neutral synergy. So now if we add ion bombardment to the picture, assuming the etch rate depends on the surface coverage theta, the ion flux, and the sputtering yield, we say, okay, let's define the etch rate in units of number of atoms that are removed per square meter per second using the ion flux, J plus. Y sub E is the yield, the maximum yield, and then theta would be the coverage, the fractional coverage in the case of the argon and the fluorine, this would be the fractional coverage of the fluorine. So this is kind of like a normal sputtering rate where you would have an ion flux multiplied times a yield. But the assumption here is the rate of sputtering depends on the coverage of an etchant like fluorine atoms. I'll talk a little bit later about what it is that's actually happening, why the presence of fluorine radicals on the surface would increase the effective sputtering yield. Um, but I'll leave that to a little later. So there's some other things going on here. This essentially is ignoring sputtering of the non-covered surface. Like the silicon atoms will also sputter with say argon ion bombardment. I've ignored that here, and also fluorine will. These are the two lower rates that John and Harold saw. You get some spontaneous etching from the radicals as well. Of course, you can add those to the up to this model, but just I'll keep it as simple as possible by not including those in this at this point. So let's apply this model. Say, well, the rate of absorption of my neutral, the Jn is now the neutral flux, say the fluorine flux. Gamma sub s is a sticking coefficient, a probability of an impacting neutral encountering a bare site, 1 minus theta, an open site. That's the rate of absorption as before. The rate of desorption now. Um, so we've included the physical sputtering of fluorine from the surface. So the ions can come in and knock off fluorine just by itself, or it can knock off silicon with fluorine present. The little x's represents the number of fluorines per silicon. So if it's SiF4, X would be 4. If it's SiF, X would be 1. And you do the same kind of algebra as before, and you calculate the steady state fractional coverage here in terms of these quantities. Now the etch rate, remember, is J plus times this fractional coverage times the yield. So if we include that in the expression, but now then divide top and bottom by J plus, you get this flux ratio Jn over J plus, and this now essentially reproduces the result that I showed earlier, that the sputtering yield is a function of the ratio of the fluxes. And by the way, interestingly enough, in this relatively simple system, and certainly in the beam system where the fluxes are relatively low, we're assuming that the etch rate is not a function of the magnitude of the flux. And in many cases, not all, we've mentioned, in a plasma, this appears to be the case as well, that the yield is only a function of the ratio of the neutral to the ion flux. Now, this can get a lot more complicated, of course. In a plasma, there's different kinds of neutral species. There are etchants, there are also deposition species in a minute, and there's different kinds of ions. It's not just argon ions. Of course, there are reactive ions. Those ions can deposit, those ions can etch, and they all have their own composition and energy dependence as well. So in detail, of course, it gets quite complex. But this is the basic idea, the basic model. It's been worked out, and it works fairly well for many cases in plasma etching. Okay, so Jane did something similar so this is now she's plotting her results as etching yield and the number of silicons per argon ions. This was for chlorine, and the plot on the left here shows she's plotted the yield as a function of the neutral chlorine radical flux divided by the argon ion flux. You remember in her beam system she had the ability to actually measure the neutral flux and the ion flux she got from like a little Faraday cup or something. So she knew what those numbers were. You can see typically it's on the order of hundreds. And then she was able, with her ion beam system, she was able to control the energy of the argon ions. And you can see this kind of Langmuir-like model. The site balance model seems to work fairly well. And then she did some experiments where she used molecular chlorine. And this is going to come up later because in our ALE work, we were using molecular chlorine and not chlorine radicals. And you can see that the model that she developed, this phenomenological site balance model, was able to see the difference between when the reactive species is, in this case for chlorine, is the radical as opposed to the molecule. By the way, it's known that molecular chlorine, and this is all for undoped or very lightly doped silicon, molecular chlorine will dissociatively chemisorb onto a silicon surface at room temperature with something approaching unity probability, and it's not quite unity exactly. I'll show an MD simulation later showing that process. Okay, And I won't go through this in great detail. This is I copied and pasted this from her dissertation where she came up with this simplified kinetics model. This is related to what I was saying earlier. The ion enhanced etching step here is this quantity beta, and the total yield. This is now the angle dependence. I'll get to that in a minute. This is not identical to the form that I showed, but it's very similar to what I showed earlier. And then what she did was she varied with different ion energies. She varied the yield, the sticking coefficient, and this ion coefficient, ion bombardment coefficient, until for the different for chlorine and CO2. And that was with those parameters, she was able to get this kind of an agreement with the experiment. Okay. Now it's also known, it's been known for a long time that of course the etching yield is also a function of ion energy. Typically, it follows a square root of ion energy functionality with a threshold energy at some point, depending upon the material. There's some results for argon on silicon, and on the right, this was Cl plus, argon plus, and this was actually an early MD result. Like my first student, Maria Barone, did this back in the mid 90s, so she got some preliminary results that were in agreement here. And then when ions come into surfaces at different angles, this is defined as 0, this is 45, well known in physical sputtering. A very typical peak here in the sputtering yield is above 60 degrees impact angle. Jane actually showed that with atomic chlorine ions, there was a rather different angle dependence, and I'll talk more a little bit about that later. For this flux ratio of Cl to Cl plus. Now in this case, the ion was an argon ion. It was chlorine. There's another effect that I'm not going to talk about today, which is that it's quite possible to have etch inhibitors. So inhibitors that would coat the sidewalls of the feature to protect the sidewalls from spontaneous etching, isotropic etching underneath the mask, extending this idea of ions only hitting the bottom of the feature. Another role that the ion bombardment would give you would be to remove, if etch inhibitor were coating the entire inner surface of the feature, the ion bombardment would also have the effect of removing that etch inhibitor at the bottom, and this would give you still better anisotropic etching results without that undercut from the spontaneous etch from the radicals. Okay, this actually, I borrowed this slide from one of John Coburn's short courses, was showing that the chemistry and the ion energy will affect both the etch and the deposition. You can get polymerization or etching depending upon the chemistry in the plasma. John and Harold developed this idea of the fluorine to carbon ratio of the gas phase etching species. So things like C2F4 versus CF4. The fluorine to the carbon ratio is much higher in the case of fluorocarbon, so CF4 rather, and so you tend more to have etching rather than deposition. But it also depends on the bias, that is the energy of the ions that are coming into the surface in the presence of the neutrals as well. And the fluorocarbon-containing plasma is also affected by addition of things like hydrogen, oxygen, and this fluorine to carbon ratio. So these are some of the complexities that occur in actual plasmas. You can, in fact, extend these phenomenological site balance models to include all these effects. But one of the big problems, of course, is you end up with a bunch of parameters in the model. And in the beam system, where Jane, for example, had a relatively few variables, she could actually fit those parameters with some confidence. And part of the problem in a plasma is you don't know the species that are coming in. You don't always know their energy distributions. You end up with all these parameters. And then the modeling activity ends up as essentially a parameter fit to various experiments. And that's not a terrible thing, but it's not as predictive as we'd like it to be. Okay, so this is where I bring in the concept of molecular dynamics, where what we'd like to be able to do is to simulate on a molecular scale the species that are impacting the surface. So basically in molecular dynamics, you have a finite set of particles, and you simulate the motion of these interacting particles through the integration of Newton's equations of motion. This is all classical. Using interatomic potentials and this is important because it's not always the case, but in this case, we need to have interatomic potentials that can account for the breaking of chemical bonds and the forming of chemical bonds. And so what one does is compute the position and momentum or velocity of n interacting atoms, n maybe thousands or maybe even tens of thousands, depending, as a function of time, given a certain set of initial conditions. The atomic motion is strictly classical. Um, when I made this slide some years ago, we were only using semi-empirical descriptions of the electronic structure based on many-body potentials, like a pair and three-body potential like Stillinger-Weber, or the so-called reactive empirical bond order method. There's also ReactFF these days. I'll just very briefly mention a little later in the talk, show you a couple of papers that where many people in this field, of course, are doing this using machine learning potentials, starting with density functional theory calculations, using various methods of machine learning, and then coming up with interatomic potentials that are more general than the ones that we've been able to do in the past. But this is the basic idea. You take the negative gradient of the interatomic potential. This is the force, mass times acceleration, and you simply integrate the equations of motion of these interacting atoms. So starting with this interatomic potential phi of r, r is the relative distance between these different atoms. Again, the negative gradient is the force. So you start off with some initial configuration of atoms, and then you go into this cycle where basically we're solving these equations of motion using finite difference. You update the positions, you take a time step, you evaluate the forces, you take a time step, you update the velocities, and you keep going around and around. Now, it's important to remember that this interatomic potential must model all reactive and non-reactive interactions, and therein kind of is the rub. It's been difficult to generalize this to more than a few atoms and a few kinds of interactions to date, hence the great interest around the world in developing these machine learning potentials, which are, in principle at least, much more generalizable, but they have their challenges as well. In these simulations, when we simulate an ion, quote unquote, coming in from the top, hitting the surface, we assume that the ions neutralize before impact. In many cases, that's probably a very good assumption. There's an Auger electron that jumps up, ionizes the positive ion, and the species that interacting with the surface is neutral. There may be cases with certain molecular ions and dielectric surfaces where that's not a great approximation. And that's one of the things that I think the community is not really fully grappled with. I could certainly say that's true of our group. So here's the thing that you need to really remember, and that's the following. The molecular dynamics simulations are resolving atomic motion literally on the femtosecond, 10 to the minus 15 second time scale. These delta T's are on the order of femtoseconds. You have a few thousand, a few tens of thousands of atoms. Now, if you're simulating the process on these picosecond timescales, and your etch is taking place over minutes, you might wonder what the heck you could possibly do that. You're not taking 10 to the power 15 time steps, right? To directly simulate the motion of atoms over a second. So the way we've gotten around this over the years is the following. We basically only simulate the impact of an ion or a radical for a relatively short period of time, typically a few picoseconds as that species comes into the cell, and I'll show you some movies of this in a minute. And then basically, if you look at the ion fluxes and the neutral fluxes, for ion fluxes, there may be a millisecond before another ion hits that 10 square nanometers or so, given the ion current densities that we have in our plasmas. It may be a microsecond if it's the neutrals, because they could have fluxes 1,000 times higher. But the impacting neutral and the impacting ion are assumed to interact only over relatively short time, these few picosecond time scales, which is 10 to the minus 12 seconds. And then essentially what you do is you jump to the next impact. So you pick a point at random on the surface, you impact it, you run it for a picosecond, you bring the surface back to 300 Kelvin, you pick another point at random, you keep doing this. You do it thousands, even tens of thousands of times. And then you get a steady state surface, and then you can collect statistics. And those are the results that you can compare to experiment. Now, you might complain and argue correctly that in some cases, ignoring these times between impacts is improper and not correct, that there are longer timescale phenomena. There's diffusion, there's desorption, there's all sorts of things, there's activated processes. Yes, of course, this is true. Our approach to simulation has been to say, let's see by making the simplest possible assumptions, the fewest assumptions, the simplest possible case, how much of the experiments can we actually reproduce without cheating? And this is what I'm going to show you here today. So let me just show you a movie here of this is now silicon. We're looking at the side view. The bottom two layers are fixed. The lateral positions are periodic, so you can see the atoms kind of jumping back and forth from side to side. We brought in a 200 eV argon ion, and the silicon atoms were color coded so that red was a more energetic species than blue. In this case, we simply removed the argon that was implanted. Now, the 200 eV has been shared to all the atoms because there's no way for energy to get out of this cell. We bring it back to 300 Kelvin, pick another point at random, and hit it again. And you do this many thousands of times. If there's no sputtering here, you can see some amorphization. If silicon starts to leave, then you may need to add more silicon at the bottom. But this is essentially how these simulations are run. So what I just showed you, we would call this a trajectory simulation. So we're looking at the impact of a single ion or multiple ions. You can also take what are called snapshot movies, and I'll show examples of those later. So at the end of each trajectory, you can take a view of the side layer or the top, but generally we do the side. And we'll do that. We may put, 1,000 of those snapshots together, and you get a view of how that a simulated surface is evolving over timescales of like on the order of seconds, which you can then compare it to experiment. We call those snapshot movies. I'll show some of those later as well. Now, the simulation needs to be able to take into account other important events such as spontaneous fluorine etching. And this was from some early results using a Tursoff type Rebo potential. This fluorine atom here, this green fluorine is coming in. It reacts with that SiF3. The whites are balls are the fluorines attached to silicon on the surface. The blue balls are silicon. I'll show this again. So this fluorine, you'll notice, is moving much more slowly than the 200 eV argon ion, of course. 300 Kelvin is 0.03 eV. It's much less energetic. So these potentials are able to model this kind of spontaneous etching. And the comparison, this is Dave Humbert's work, goes back into the early 2000s. There's a comparison to other beam experiments. It's in reasonably good agreement. Okay. Now I'm going to talk a bit more about chlorine. I decided to use this simulation. This was done by Jack Draney and my group right now. So you can see these are two relatively recent papers, 2025, and one just came out. They're both 2025, where we were using this deep potential MD approach that Roberta Carr here at Princeton has developed. A number of folks at Princeton are using it. I won't go into great detail. There are some issues with transferability of these potentials. This is definitely not a solved problem. But Jack had done these deep MD calculations, which are based on DFT calculations. And so after he created these classical machine learning potentials, he did the simulation, in this case, showing chlorine coming in, molecular chlorine, at its dissociative chemisorption on its silicon. It's a 100 2x1 reconstructed surface. And he actually was able to go back to the DFT calculations and provide the electron density. The electron density was, of course, part of the density functional theory calculation. And if you go back to ab initio DFT calculations that were done back in the early 2000s, they look very much like this. These are much faster than those calculations. But yeah. Okay. So again, this is the scheme. This is now our silicon layer from the side. Just pointing out that typically a number of maybe 3 or 4 nanometers wide. This one happened to be 5 nanometers deep. Again, this business of just simulating over a certain period of time. The impacting species come in from above. This is by the way a snapshot movie. These little gray balls are now or green ones are the silicons. This is Joey Vella's work, postdoc who's now at Tokyo Electron. And then he turned on the argon ions. And I'll talk more about this amorphization and mixing in a minute. But the radical ion impact, you choose these positions at random on the surface. You simulate for a few picoseconds. You do a product sweep. That is, you get rid of any products that are there. We thermostat, bring the layer back to 300 Kelvin, record the image for the movie, just do this many, 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 many times. And here's some papers that describe this was a review paper that I did with Pascal Bro in Orléans back in 2009. This was Bouchon work with Emily Despau in Grenoble. And then this was one of Joey's references. So again, we focus on these prompt impact processes on the picosecond to perhaps as much as nanosecond timescale. And this is how we're able to take the EMD simulations and address the timescales that are relevant to experiments. Okay, so Joey basically tried to compare his MD simulations to Jane's results. And you can see that these open symbols with the error bars were Joey's results. This was the squares here were 100 EV and then 60 EV and 35 EV. And you can see the agreement isn't perfect with the MD between the MD and the beam experiments and again the site balance model and the dotted lines here, but they're pretty good. By the way, there's no adjusting of parameters after you set the potential parameter for the silicon and chlorine interactions and the argon chlorine argon silicon interactions. You don't change anything. There's no adjusting of parameters after that. Joey then looked at this etch yield as a function of angle of incidence. In this case, this was the argonine with a flux ratio of 600. Again, you can see he's capturing that variation of etch yield with angle reasonably well, but not perfectly. Another example where he brought in chlorine ions, I mentioned before. Now this is plotted as a square root of ion energy. The Tachi experiments are the black squares, and then Jane, this should be Sawan, with the triangles, and then Joey's MD experiments were here. So again, there's some variation from one experiment to the next, but the MD simulations are capturing this energy dependence rather well, and the threshold, it appears. And then when Joey brought in molecular chlorine as opposed to atomic chlorine, this was from the previous plot. This was the 100 EV case that Jane was using with the chlorine radicals, and Joey's results were these open squares. When Joey used molecular chlorine and compared to Jane's results, you see this factor was reasonably well captured by the MD simulation. I want to mention there are other groups around the world. Satoshi Hamaguchi and his team at Osaka University have done similar kinds of MD and beam experiments with some good results here. And this is from Emily's group and Olivier Joubert in Grenoble, where they were doing something similar, bringing in chlorine, molecular chlorine, atomic chlorine, and the relevant ions, again using the same kind of MD simulation. And they were looking at this mixed layer of silicon chloride as a function of ion energy. They were particularly interested in making sure that layer was as thin as possible. And their MD simulations are shown here with a couple of experiments shown here as a function of ion energy. And you can see that these simulations are approximately capturing what's going on in the experiments. So let's summarize a little bit of what we think we've learned by comparing these MD simulations to experiment. So the assumptions and approximations which are inevitable in the MD simulation, starting with the approximate interatomic potential to the time and length scales that are inevitable for these calculations, seem reasonably valid for just following these prompt processes. That is the ion impact induced processes following the ion bombardment and the barrierless neutral molecule interaction with surface. That is, so when a fluorine or a chlorine comes into a surface, there's no activation energy barrier. They just come in and they attach to a dangling bond, for example. If those are the important processes that are occurring, it seems like these kinds of MD simulations, without cheating, without fooling with parameters, can actually reproduce rather well. They also support and match the site balance models and give more legitimacy, perhaps, to these phenomenological models that have been used historically to correlate many sets of etch data, and are often used in feature profile simulations. And I'm going to come back to a little bit briefly later in the atomic layer etching and show that you can actually use a transient site balance to understand some of those results as well. And I'll say a few things about the limitations and challenges later. I've mentioned a few of them already. Okay, so let's turn to atomic layer etching. This is a schematic. Joey put this together. Basically, so if say you're etching silicon and you have molecular chlorine, if the molecular chlorine dissociatively chemisorbs, self-limits, you only have a monolayer of chlorine, and then you bring in the argonines, and the argonines promote the desorption of silicon chlorides, and nothing happens underneath. The silicon remains crystalline every place else. And then you go back and you just do it again and again. You can etch etch the system layer by layer. This is kind of the ideal cartoonish version of what's going on. And we set out to see if we could understand what the MD simulations would tell us. Now, it's important to compare results to experiment, and this is where we got lucky with Vince Donnelly at the University of Houston, who happened to be doing some experiments. Samsung, I think, was supporting them at the same time, doing something very similar. And so we hooked up with Vince and his team, and they were using an inductively coupled plasma. They had a laser interferometer, so they could measure the thickness of the silicon film as the etching was occurring. And they had an optical emission spectrometer set up, so they focused on the products just coming off the surface. So during the argon ion bombardment step, as I'll mention, in this atomic layer etching, they could actually see the products coming off the surface, and it turns out that that's actually directly relatable to the MD predictions of this. And this is what we set out to do. So just describing the flows and the power that they used. So this is a 7-second cycle. This is in Joey's paper from 2023. So in the first 2 seconds, the DC self-bias is the red. So this is just chlorine flow. So there's no chlorine plasma. This is just molecular chlorine flow. There is a little bit of a variation of pressure. You can see these green squares. You can see that it went from 20 to a little about 21.5 millitorr because you're turning the gases on and off. This is the chlorine flow step where you just chlorinate the surface. The plasma is off, the bias is off. And then at second 2, the chlorine flow has stopped. Chlorine flow is 0. The argon flow continues throughout, and the plasma is turned on. The ICP is on with bias. And this is where much of the etching occurs. And then they looked at a case where the ICP was on, the plasma was on, and there was some floating potential and some potential from the coil, but the bias was off. And then at the step 4, the chlorine flow is off, the plasma is off, etc. That's for a second. Then they go back and turn the Cl2 on again. And what they were looking at is both from the laser interferometry, they were seeing how much silicon was etching at what times, and they were looking at the optical emission of the products. So here's an example of, again, this cycle shown here. This is now the optical emission from different species. The silicon is in the dash line here, this blue dash line. And then they looked at silicon chlorine, SiCl, and SiCl2. These are the major products. They saw no SiCl3 and no SiCl4. And when the argon ion bombardment starts, you see a big jump in the emission of the chlorinated species. Silicon comes up as well. And then this is when the plasma goes off. Sorry, the bias goes off here, and then the plasma goes off. And this is now the rechlorination. And it's done. This is 3 different times. So you see this big jump in the chlorinated silicon products coming off the surface, kind of a square wave, if you will, for the silicon atoms. And then there's something funky that happens when the plasma is on, but the bias is off, and then comes back up again. I probably won't spend too much time on this. What I'm going to primarily talk about is this initial pulse of chlorinated silicon products. Yeah. Okay. So in the interest of time, I think I'm not going to go through all this detail precisely how we did this. I just want to show you some of the main results now. So now what I'm showing you here is the side view. These yellow balls are the silicon, the green balls are the chlorine. This is after several cycles has occurred, so there's still some chlorine mixed in the layer. Molecular chlorine has been exposed to the surface, and so the surface is a bit more than a monolayer of chlorine. And this is now after a monolayer of fluence. One monolayer, by the way, is defined as 10 to the 15th ions per square centimeter. And you can see that some of the chlorine has been mixed into the layer, and some of the chlorine has been removed from that top surface. Now here's at 5 monolayers, 10 monolayers, 25, and 50. And by 50, you can see that most of the chlorine is gone. This, I believe, was 100 EV. Yeah, this is 100 EV argon ions. And so the argon is amorphizing that layer to on the order of a nanometer. And the chlorine that is absorbed at the surface, some of it gets mixed into that amorphized layer, but eventually, after enough ion impacts, silicon is sputtered and the chlorine is sputtered, and we come back to almost no chlorine there. So again, you get a significant amorphous region formed with nearly uniform chlorine. And after this initial impact, the chlorine mixes very, very quickly. Of course, this doesn't look at all like the ideal case. Now, it's true these are 100 eV argon ions, and you can lower the ion energy to reduce the thickness of this amorphous layer, but you never completely get rid of it. Um, and the other thing is this near surface region continuously changes with time and depth with ion fluence. That's something I think was not fully appreciated in the community. And if you look at the top, this is now the top view. You can see this is the chlorine. Here's the chlorine that we're seeing on the side view here. You can see it's just covering this the surface. This is now the top view after one monolayer, 5, 10, 25, and now this is 50 where there's only a few chlorine atoms at the top. So if we plot now as a function of cycle number, on the right, it's the chlorine coverage. So this first red is the coverage of chlorine. It goes up to about 0.8 monolayers of chlorine on the surface. And then at this point, the argon ions hit at 100 eV. The blue is the silicon etch. You can see that when the argon ions hit, the chlorine coverage drops, of course. That's getting sputtered away. And the silicon loss has increased. And then now this is a cycle. The next cycle, chlorine comes up, is now approaching a monolayer on the surface. Argon ions remove the chlorine, remove more silicon, and this continues. And it reaches this approximate steady state after about 3 or 4 cycles. So the schematic of what the MD simulation is telling us is that there's this mixed layer. The argon ions are bombarding the layer. It's mixing the chlorine. The chlorine can be absorbed to the surface, but it's the argon ions are mixing the chlorine into that layer and then are also sputtering chlorine, sputtering silicon, and sputtering silicon chloride. The sputtering of silicon atoms and chlorine atoms was, I think, a surprise for some of our industrial colleagues. And then as of course this etches down, effectively the silicon's coming up into that layer. Okay. And so this is now one of these snapshot animations where the side view of the layer is just shown again and again and again. You see this chlorine happen to get particularly deep for some reason. You can see after this initial adsorption of chlorine at the surface, this was after the 4th or 5th cycle or something like that. You can see that the chlorine is pretty much uniformly mixed into this amorphous layer and is slowly being lost from the layer as the silicon and the chlorine are removed. And you can see that it almost looks as if this layer is kind of liquefied in a certain sense. And in a certain way, I think you might think of that. Certainly, ion bombardment is inducing mixing and motion of both the silicon atoms in this amorphous region as well as the chlorine. Okay. One way we also compared to the experiment was in the etch per cycle. This is nanometers per cycle as a function of ion energy. The red symbols are Joey's MD simulations, and you can see that we underpredicted a bit the etch per cycle at the higher energies for reasons I'm not completely sure why that happened. We don't know the exact ion energy. For one thing, the MD simulations assume that the ions come in at a single ion energy and at a single angle, which is perfectly normal to the surface, and that's not quite the same as in Vince's experiments. And it might account for something like this factor of 2 at the higher energies. I'm not sure yet exactly what's accounting for that, but it's approximately right. So here's the key result. So this is now a plot of the optical emission. This is proportional to the optical emission. This is now for silicon atoms for 3 different ion energies, 250 eV, 80 EV, and 45 EV. This is a function of ion dose or time. This represents a few seconds of plasma exposure. You can see that the silicon atoms come up and then reach this plateau. And the MD simulations, while not exactly the same, are very close. By the way, these were normalized to the 80 EV case. So Joey said, all right, let's just make these arbitrarily because the optical emission doesn't give you absolute numbers. If we made the 80 EV result 1, and then we say, okay, let 80 EV be 1. So 80 down to 45 is similar to what they saw experimentally. And then from 80 up to 15, Joey's predicting a factor of about 7. Vince's results is a factor of about 5. But it's really capturing the results probably within the accuracy that you could expect. By the way, the silicon atom emission is affected by dissociative excitation of SiCl. We corrected for that to get just the silicon atom emission just from ground state silicon. If you now look at the comparison of for SiCl and SiCl2, again, as a function of dose, this is for the 45 eV case. Now what I'm doing is plotting the optical emission results in the solid squares, Joey's MD results in the open squares. This is at 45 eV on both of them. You can see the agreement's actually pretty good. And then at 80 eV, again, with the normalization that I mentioned earlier, the solid symbols are the emission and the open symbols are the MD. And then finally at 215 eV, once again, um, the agreement between the simulation and the experiment is quite good. So if you normalize to the 80 EV results, but going down to 35 EV, or in this case 45 EV, is an absolute comparison. Going up to 215 is an absolute comparison. Actually, to tell you the truth, I was surprised that it agreed this well. It really did this quite well. There was one complication that took us a while to figure out. It turns out that chlorine will come off the walls during the argon ion phase, and you have to account for that. If you eliminate that, of course, that was not included in the EMD simulations, and the agreement's actually pretty good. Chlorine atoms, it was difficult to get the chlorine atom results, so they only got one set of results at 70. Ours at 80 were pretty similar. Again, normalizing to the peak value at 1, the MD simulation is capturing the chlorine atoms being sputtered as well. And this is now the comparison between the silicon atoms. Again, the solid symbols being the experiments and the open symbols being the MD. I'm not going to talk about this very much, but we realized that what we could do with these calculations is that we could actually use a transient version of the site balance model that Jane described. And Joy put this paper together, came out 2024. I won't go into detail about this, but again, this was in collaboration with Vince and his group at Houston. But you can, in fact, fit parameters into a site balance model where, of course, the coverage, the theta of Cl will change with time as the argon ions hit the surface. But this was easy to account for. To generalize that steady state model to a transient was relatively straightforward. We also did something similar more recently. This is Jaehan Kwan's recent results, which just came out. We said, well, can we actually solve reaction diffusion equations that take into account the spatial variation of the concentration as a function of depth? Again, I won't go into detail, but that appears to work fairly well as well. So one reason for the site balance model and the continuum modeling is in these reduced order models is that when you translate this to our industrial colleagues, where they're trying to do things like feature shape evolution and so on, you can't do MD simulations. So we need to have a calculation method which can work on those scales. That's a whole separate topic. So just summarizing this part, we got actually surprisingly good agreement with respect to etch per cycle and product distributions when we took into account these wall desorption effects. These MD simulations, especially after the experimental validation, gives us some key insights into mechanisms. This ion-induced mixing region, ion interdependent, is important for this plasma-assisted ALE. And these reduced order models, such as parameterized site balance models or diffusion reaction models, can be developed and parameterized based on the MD simulations. But I think one of the big messages here is that you really need to work hard to find good experiments to compare the calculations to convince yourself that the calculations are right, because all these simulations involve assumptions and approximations. Okay, so let me switch to the second ALE study, which was for diamonds, is relatively recently. I was very lucky that Natalie de Leon here at Princeton in electrical and computer engineering is interested in quantum diamond. These nitrogen vacancy centers are really good quantum sensors, especially for magnetic fields. The problem is that the coherence time drops off if that sensor is if the NV center is close to the surface due to noise from roughness or contamination or surface spins or various things. And so the nanoscale sensing, where you'd like to be able to use these, for example, to do single molecular NMR or something like that, like for a protein or something, the sensitivity is compromised. And so you really need to be very careful with the surface. So we thought, well, what about atomic layer etching? Maybe that could help this process. Again, as she points out, low disorder, low damage surface termination is the key. And the current process that they use, it turns out to be quite laborious. They'd like to end up with a perfect diamond surface. This is now 100 with this. This is the oxygen bond, the COC bond at the top, this ether bond They get this through this so-called triacid cleaning. This is still work that's really kind of ongoing, but the idea is, can we replace some of these liquid boiling in acids and so forth with a plasma process? So we have this idea of using plasma-assisted atomic layer etching of single crystal diamond. In this case now, we're talking about bringing in somewhat energetic O, as well as argon ions, and I'll describe in a little bit greater detail. First, I want to talk about our simulations of argon ions and energetic O on diamond surfaces, and then we'll do the sequential ALE cycle that I'll describe in a minute. So the first thing we did was simply just look at argon sputtering yield on diamond as a function of energy and compared to various experimental results. Although the available data aren't extensive, we got reasonably good agreement. This new potential, by the way, is a ReactFF potential. This is Jack Draney's work. Jack was using this DeepMD method and active learning approaches that machine learning tools use. But then we use the DFT calculations to fit the parameters in a ReactFF potential. I won't go into detail on that in the interest of time today. Then he looked at this amorphization. So if you look at argon ions at say 100 eV, we would predict amorphized to about 12 angstrom thickness. Some results from Kong et al. Back in 1991 showed similar results. And if you put it in terms of a monolayer, you get the results shown here on the right. Now, one of the things that's particularly interesting about argon ion bombardment on silicon or carbon, now you're looking at the side view of a diamond carbon 100 surface, and Jack put this step in the carbon atom profile, and then just put these periodic surfaces together. And so, well, what happens if you hit this with argon ions at 100 eV? And the red balls are the amorphous carbon, the non-diamond carbon. And the point is, if you impact the surface, you see the periodic boundary shown here, so you have multiple images. But you have basically it has a tendency to essentially smooth out the surface. It almost looks like there's a kind of a surface tension effect. With enough impacts, you get this on the order of a fraction of a nanometer thick amorphous layer. The argon ion bombardment has smoothed the surface. And so we said, well, what if we kind of reverse the atomic layer etching and say, if we impact the diamond layer initially, maybe it's a little bit rough, maybe it's a little bit dirty, you impact it with argon ions, you amorphize the surface and you smooth it out, and then come back with oxygen ions, carefully energy controlled, can you etch back the amorphous carbon selectively and end up with a nice smooth diamond surface? And that was basically what Jack set out to do. This is now an image of an oxygen coming into a carbon 100 2x1 reconstructed surface, just showing the simulation of the adsorption of the oxygen in this case. And eventually we'll get a full coverage just to illustrate what that would look like. Now, if you bring energetic oxygen into diamond at 1 eV, 5 eV, 10 eV, 25 or 50, at 1 eV, the blue balls are the oxygen, and 5 eV, and even up to 10 eV, you don't get any or very little amorphization. So the red balls are the non-diamond carbon. At 25, between 10 and 25 eV, those O pluses start to damage the layer. You get this sp2 carbon, and you especially see this at 50 eV. So one of the most important results that Jack found, and this is actually consistent with what people knew in the literature already, is that if you look at the etch yield of diamond carbon or amorphous carbon per O plus as a function of energy, now the red symbols are from a layer that had been pre-amorphized by ion bombardment. So it was a relatively thick amorphous layer. And Jack showed that from 10 down to even 1 eV, O plus will etch the amorphous carbon quite readily. But the 100 diamond surface doesn't etch until you get somewhere between 5 and 10 eV. And so the selectivity is essentially infinite for O plus if this O plus energy is less than about 5 eV. Set aside for the moment the problem of controlling ion energies to that level in a plasma first, but we said, well, we should be able to take advantage of this extraordinary selectivity for a novel ALE scheme for diamond. So what I'll show you is a sequence where the first sequence, Jack will expose the surface just to O plus. It gets about a monolayer of oxygen on the surface. And then the argon ions exposure, you create, in this case, two monolayers or so of amorphous carbon. And there's a certain amount of etching during that period of time, and the oxygen drops off. And then you hit it with O plus again. And this is the key step where the oxygen, 5 eV in this case, is predicted to remove that amorphous carbon, etch away that amorphous carbon, and then reestablish a monolayer of oxygen. Come in again with the argon ions, again, reestablish the amorphous carbon, and so forth. Now, I think in this example, Jack was using 50 eV argon ions. You could use much lower energy than that and just have the amorphous layer be substantially smaller. And this is actually a result from his actual calculation with 5 eV O plus and 50 eV argon, and it does appear to work. He starts by getting oxygen onto the surface with 5 eV O plus, creates this amorphous layer of about 4 monolayers with 50 eV argon ions, etches that amorphous layer that now with some tens of monolayers of O plus at 5 eV, removing essentially all of the amorphous carbon, retaining a monolayer of oxygen on the surface. So let me show you the movies of this. And we end with this O-covered diamond layer. So this is a side view of the layer. So the initial exposure of 5 eV, this is now the 5 eV oxygen. Let's just repeat here. You just get the monolayer of oxygen and it stops. It's self-limiting. 5 eV will not etch the underlying 100 diamond carbon. And this is what it looks like in practice. The more purple balls are ether bonded carbon-oxygen carbon. This is a carbonyl, a C double bond O bond. At the end of the day, we actually want mostly ether. That was step one. And then the next step is to amorphize it. You can see the side layer here. The argon ions create, some fraction of a nanometer thick layer of amorphous sp2 bonded carbon, and it gets rid of most of the oxygen, and some of the carbon etches away. But now the key step, and this is now the movie of that, so you can see the buildup of the amorphous carbon and some of the oxygen that's mixed in. Now the key step here is with the 5 EVO, do you etch back this amorphous carbon? And you can see from the layer that it does that. And furthermore, it seems to be smoothing the surface as well. Show this again. So what the simulations are predicting is you etch away the amorphous carbon, you maintain a monolayer of oxygen on the surface, and somewhat to my surprise, these 5 EVO atoms appear to actually smooth the initially somewhat rough diamond surface. And I won't have time to talk about it today, but at this energy, what Jack was able to show was that the 5 EVO will etch at the edge of a terrace and actually remove a single terrace of diamond 100. And now here's the movie of the snapshot movie, removing the amorphous carbon. Much of the oxygen is carbonyl, the C double bond O, but then by the end of and you can see some of this removal of the terraces. Much of the layer is the desired ether bonding. So if we plot as a function of exposure O plus, argon O plus, the ketone is in the blue and the ether is in the green. And in particular, at the end of the O plus, we're getting about 70% or so of the desired ether bonding and 30% or so of the ketone. We've not had a chance to compare this to experiment yet. We're in the process of trying to do that. Natalie's gang here at Princeton, what they call the Princeton method, and this long process that takes days and days, they're able to get a full oxygen monolayer with a relatively low carbonyl coverage. In this initial calculation with our simulation, we're down around here, around 25 or 30%, which actually was better than I expected. But this is the goal, is to see if can we use a plasma process, this ALE, to get a very smooth surface with the kind of surface bonding that we want. Okay, just to point out that, in fact, there's a lot of other processes that are occurring in the plasma. I haven't talked about photons. I haven't talked about electrons. There's a lot of other things happening that in general is still very much an open question in our community. So let me just summarize a bit. I think we've been able to show that these classical molecular dynamics simulations of surfaces are on the order of 10 square nanometers, maybe 5 nanometers deep, following picosecond timescale processes in the atomistic simulations, can capture many important processes in these low temperature plasma surface interactions. That is, these prompt processes often dominate, not always, but they often do. However, we know that there are longer timescale activated thermal processes, surface diffusion, etc., that can require also, I haven't said anything about explicit charges, explicit fields, photons, electronic excitation. All of these things are known to be important in some cases. None of that is in the simulation that I've showed today. These effects need to be studied and incorporated in future atomistic simulations. Probably the most important immediate need is a systematic and reliable way to develop suitable interatomic potentials, which are transferable. So I'll describe in a minute. For any combination of atoms in etching, you may have 7 or 8 different atoms. We can't do that yet. Lots of people around the world are trying to develop these machine learning methods. They're promising. Different machine learning methods have different kind of transferability. But by transferability, I mean you fit a potential using DeepMD or something like that for one set of conditions, say one energy, one angle, radicals versus molecules. But then if you change the conditions just a little bit, the potentials don't work anymore, and you have to refit the potentials. That's a potential that's not very transferable because there's no physics in those models. So it's a whole subject in its own right. I'm far from an expert in this, but as I say, there's a lot of work around the world in computational material science to do a better job of this. A lot of people are working on this, and hopefully, I'm sure the community will come up with better solutions as we go forward. So one of the things that people have talked about but not much is done with these very sort of nanoscale. This I bought. I think Eric Joseph from IBM gave this to me a while ago. A certain kind of structure. You can see the link scales here. It's not impossible to imagine doing direct simulation for these nanoscale features, and I think you should be able to do these direct NB simulations for features that are this small. That's certainly something that we could be doing. Others could be doing. We haven't really done it yet. Okay, so with that, I'm gonna finish. I will stop sharing. I hope you guys are all still there.
Thank you very much, David, for this insightful presentation.